Section 5.1 covers normal distributions. We're going to back up a little bit and talk about some general continuous distribution properties first, and then more specifically, we can get into normal distributions. A continuous distribution has uncountably many possible values, so you can't list them all out with their probabilities in a table or anything like that. And there are some consequences of having uncountably many possible values. One is that the probability of any individual number is zero, which means then that probabilities won't be assigned to individual values, they'll be assigned to intervals. And if you look at the last couple of points there, it looks like there's going to be some integration here, the area under the curve. The area under the curve idea is right, and generally for a continuous distribution, you would integrate to get that. But a normal distribution doesn't have a closed form of its integral. So there is a function that you can write out to specify a normal distribution, but you can't integrate it by any conventional methods. That's why calculators and software and things like that are typically used to do it. Everything on this slide is made up, but I needed a prop to work with. So if X is the weekly use of gasoline by adults in North America, and the probability that X is strictly between 7 and 9 is 0.24. Then if you look at the picture, the way the probability is being determined is the area under the curve between 7 and 9. Then there's the question at the bottom, what's the probability that a randomly chosen adult in North America uses exactly 7 gallons of gas per week? Well, that's a specific value, so it's 0. So the probability that X equals 7 is 0. By the same sort of logic, the probability that X equals 9 is also 0. But then consequently, all of those compound inequality statements are equivalent to the probability that X is strictly between 7 and 9. You can include the endpoints or not include the endpoints, and you're going to end up with the same thing, since the probability that you get either endpoint exactly is 0. The general consequence of this is that for normal probabilities and for t probabilities, so all of the probability functions that we're going to have to use in Chapter 6, there's no difference between less than and less than or equal to, because the only difference there is either including the endpoint or not, but the probability of the endpoint is 0, so you would get the same thing either way. Same thing with greater than and greater than or equal to. The only difference is the endpoint, and the probability would be 0 of getting that endpoint exactly. That's a weird idea that less than or equal to end up being interchangeable, and the same thing with greater than and greater than or equal to, but for continuous distributions, that's the way that it works. The idea of a density curve, that's the curve that's drawn to represent the probability distribution. And it is a theoretical model, which is why you get a nice perfect shape. That's why a normal distribution is going to be a nice perfect bell curve. And the way that you would determine the probability is by figuring out the area under the curve for whatever interval you're interested in. Normal distribution, it is an idealized shape, so it's perfectly symmetric, it's bell-shaped, and it's characterized by two things, the mean and the standard deviation. It's always going to be that shape. So if you know what the mean is, that's going to tell you where it's centered, because if it's perfectly symmetric, the mean and the median would be the same number. So that's going to tell you where it's centered, knowing what the mean is, and then the standard deviation will give you an idea of how spread out it is. Because if you have a small standard deviation, then the bell is really tall and thin, but if you have a big standard deviation, then it's short and really stretched out. The notation the book uses is inside that box with the x tilde, then n for normal distribution, and then specifying the mean and standard deviation, whatever they are. There is a way that you could effectively compute normal distribution probabilities by hand if you use Simpson's rule, but that takes a lot longer, so we're going to use technology, and really we're going to focus on using StatKey, although you can use R to do it, you can use Excel to do it, you can use a calculator to do it, as long as you have one that supports probability functions. So there are a lot of things you could actually use here, but we're going to focus on StatKey. This example is going to exhaust the three possibilities as far as what type of inequality you might have to deal with. The duration of a flight between two cities, normally distributed with a mean of 4.6 hours, standard deviation of 0.3 of an hour. And then there are three probabilities that we want to figure out. The first one, the probability that the flight takes less than 4 hours, that's what you get in StatKey. You can't see it here, but you have to specify the mean and standard deviation for that normal distribution. Less than would be toward the left. So if you look in the upper left corner, I have left tail checked, and then I just specified the bound for that left tail is 4. To do it for real in StatKey, and this way you can see the specifying of the mean and standard deviation, where you want to be is where it says theoretical distributions, normal. So this right here. Then the mean and standard deviation were not 0 and 1, they were 4.6 and 0.3, so I need to change those. If you click on Edit Parameters, you can do that. And then less than was a left tail, and bounded at 4. There. You get 0.023, just like in the PowerPoint. The next probability was for more than 4.5 hours, so more than would be a greater than, which means the cutoff should be 4.5, and we want everything to the right underneath the curve, so that part that's shaded red in the picture. If you look in the upper left, I have right tail selected, and then I just specified the bound of 4.5. To do this in StatKey, I don't want left tail anymore. Now I want right tail, and I want the bound to be 4.5. And there's the 0.631, just like in the PowerPoint. A compound inequality between 4 and 5. It seems like you might want to pick two-tail here. You don't, because if you pick two-tail, that's when if you change one tail, the other tail will change sympathetically to make sure that you're getting something symmetric. You don't necessarily want that. Instead of picking two-tail, I would pick left tail and right tail simultaneously, because then you can adjust those tails individually, and that's going to work out a whole lot better in the long run. If you look in the upper left corner, I have left tail and right tail selected. That way I could adjust the two tails individually to get what I want. The one slight drawback is that now the thing that I'm trying to get is the part that's not shaded in. The part that I want is in between 4 and 5, so it's the 0.886. That's slightly different than the way it normally works, but I think that's a very minor problem. Doing it in StatKey, I have right tail selected. I also need left tail. The left tail bound is where it's supposed to be, but then the right tail bound has to be changed to 5. There, 0.886, just like in the PowerPoint. Percentiles are next. This is effectively the inverse function of finding a probability, because when you find a probability, you're given the cutoffs, and then you're getting the area under the curve. When you're finding a percentile, effectively you're given the area under the curve, and you're trying to find the cutoff. So what you do here is kind of the reverse of the thing that we were just talking about. In general, the pth percentile of a distribution is the value with p% of the observations below it. So like it says there, 35th percentile has 35% of the data below it, 80th percentile has 80% below it, and so forth. You can use a lot of different things to get percentiles, like it says in parentheses, R, Excel, calculators, but we're going to focus on StatKey just like we did with the probabilities. The example at the bottom, the weight of adult turkeys normally distributed with a mean of 22 pounds, standard deviation of 5 pounds, and then there are a couple of percentiles that we want to figure out. By definition, the 75th percentile has 75% of the data below it, so I want a left tail with 0.75 in the left tail. Here, that's the thing that I'm specifying, and the answer is the 25.372. To run through this in StatKey, again, theoretical distribution's normal, and now I need to change my mean and standard deviation to 22 and 5. And it's a left tail where you want 0.75 for 75th percentile in the left tail. And there's the 25.372. The other question, the cutoff for the heaviest 10%, this is where maybe you have to watch out a little bit. That's not the 10th percentile. It's the 90th, because the percentiles are named by what's below that value or graphically what's to the left. If it's the cutoff for the top 10%, there's 10% above it, so 90% below it. So that's the 90th percentile. Although you could get it by specifying 10% in the right tail instead of 90% in the left tail. Either way, you're going to end up with the same answer. I'll show you what I mean in StatKey. Since it's the 90th percentile, I could put a 0.9 in here, and I'll get the 28.408. Or, if I specify a right tail with 0.1, same thing, 28.408. So either way would work here. This is going to look redundant right now, but it's not. However, it's going to look redundant because the application for where you would need the standard normal distribution is a thing that we haven't done yet. It's everything that has to deal with proportions in Chapter 6, which would be sections 6.1 through 6.3 and 6.7 through 6.9. That's where you really need a standard normal distribution, although for right now, I'm well aware that it's going to look like extra work. Just trust me, it's not. There's a point later where you need it. But a standard normal distribution, it's a normal distribution, just a specific one. It's one where the mean is 0 and the standard deviation is 1. And you can always transform any other normal distribution into a standard normal by standardization, where basically what you do is subtract the mean and divide by the standard deviation, just like it says there. And symbolically, z equals x minus mu over sigma. You're going to see that z notation a lot when we get into chapter 6. Z is typically what you would use for a standard normal distribution. Going back to the turkey example, if x denotes the weight of a randomly selected adult turkey, we know that x is normally distributed with a mean of 22, standard deviation of 5. So if we wanted to find the probability that x is greater than 20, you could do it directly, or you could do it by transforming to a standard normal. The one on the left, where it says the probability that x is greater than 20, you can do it directly like that, with the mean set equal to 22 and the standard deviation set equal to 5. The next step is standardizing, so that middle part in between the two equal signs. When you standardize x, you get z. So x minus mu over sigma, you end up with a z to the left of the inequality. And then on the right side, subtracting 22 and then dividing by 5, you'd eventually end up with a negative 0.4. This is what you get without the transformation. So this is from StatKey with the mean specified as 22 and the standard deviation specified as 5. And then the cutoff would be 20. Then this picture is when the transformation's been done. So instead of a normal distribution with a mean of 22 and a standard deviation of 5, this is a standard normal, but now the cutoff is going to be what you get when you standardize 20, which was negative 0.4. You get the same answer. It's 0.655 either way. One other thing with the standard normal distribution is that if that phrase is ever used, so if there's ever a homework question that uses the phrase standard normal, the mean is 0 and the standard deviation is 1. Those things probably won't be explicitly stated, but if it's standard normal, that's the way that it works.